Hi everyone, so my name's Jonathan. I'm joined here today with Pooja, and so today we'd like to look at how architecture can go beyond data as a means to address climate change. So this really involves redefining the way in which we as architects design the built environment to ensure that it adapts alongside our lifestyles and our changing social needs. So in our MArch thesis, the P2 Tower, we examined how using people's sociability as a driver for design enables architecture to continuously evolve to meet their needs and improve urban livability. So within architecture, there exists this paradox, which lies in the fact that over time, people's sociability changes, yet the buildings they occupy do not change to accommodate their new needs. And densification around the world has increased this problem because architects have responded to the immediate challenges instead of looking for lasting solutions. And this problem is only projected to worsen in the future, particularly in Hong Kong. In Hong Kong, rapid densification focused solely on private spaces, leading to the proliferation of the Hong Kong tower block. Yet the rigidity of the tower block prevents spaces from meeting people's sociability needs over time, and this has detrimentally impacted the quality of life for people. And this is evident when viewed through the lens of unauthorized built works, which are secondary structures built onto existing buildings by its occupants to provide lacking spatial and programmatic needs. So numerous architects and urban designers have attempted to tackle these challenges throughout history, but most of these proposals sought immutable solutions to immediate challenges. Therefore, our thesis developed the idea of an evolving architecture, which was a computational workflow which generated a new housing typology for towers and an urban network system that met the density needs of cities while also facilitating continuous spatial changes as people's needs changed over time. So when we talk about sociability, the terms public and private, we're looking at them specifically in terms of sociability. So based upon this notion and existing research, we developed a system which enables us to quantify this sociability of a space, particularly as it changes over time. And this enables us to adapt a space to meet people's changing needs. Our system operated based on a series of measurable parameters that were within an architect's scope of work. And here you can see a few examples of how those were measured. The focus of these parameters was split between two phases. The first phase began with the design of the fixed systems of the tower morphology and the structural system. From there, the design examined the adaptability of the tower at three different time scales: the public-private segmentation over the course of decades, the program topology over the span of multiple years, and the spatial organization over the timescale of a few months. These adaptable systems were enabled by a novel fabrication system which combined concrete robotic 3D printing and traditional bamboo weaving techniques. Then during the second phase, we revisited those sociability parameters and our spectrum to develop a micro-urban network that connected the tower to its local context and an urban network that connected multiple towers together across the entire city.
We developed the thesis across multiple distinct scales, but today we're going to focus on two specific ones that were most crucial to integrating sociability as a driver of design. In the tower design, we implemented sociability through the lens of public and private spaces, while on the urban scale, we focused more on integrating social interaction as a driver of design. First, we'll look at the tower scale. The main goal at this scale was to determine the major programmatic locations of the tower's public and private zones. Typically, Hong Kong's tower block focused mostly on private spaces, which dominated the majority of the tower section. This often left public zones to be merely leftover spaces. So to counter this, the P2 tower required a different approach to strike a balance between these public and private spaces. And so to facilitate that, we used a co-evolutionary algorithm. This expands on traditional multi-objective optimization processes by introducing two interconnected populations, which essentially evolve in parallel. And through this process, the two systems share data to inform their optimizations. And so in our case, these two populations represent the public and private spaces within that tower system. And of the three major types of co-EAs, or co-evolutionary algorithms, we focused on mutualism, where both populations support each other's fitness objectives to ensure that ideal team scenario. And since there were limitations on existing engines which support co-EAs, we decided to develop our own plugin for Grasshopper to enable that parallel evolution. So this engine that we made cycles between two states. First, it optimized each population independently, and then optimized their shared parameters collectively. Then they were evaluated as a unit to ensure that collaborative optimization process. And we ran this algorithm using fitness objectives related to increasing density and increasing connectivity for each population, among other ones as well. Initial experiments showcased the algorithm's potential to be a powerful tool for optimizing such complex systems in a cohesive manner. And while the results didn't show a perfect optimization process, it was observed that these two independent populations began to converge alongside their shared fitness criteria. And in comparing this methodology to the traditional optimization processes, the results showcased how that CoEA addressed common pitfalls by dissecting complex problems into manageable parts. And so in doing so, we were able to develop a tower system which more comprehensively addressed those needs for both public and private systems together, which enabled a more diverse system driven by the social design. Next, we'll take a look at how sociability drove design at the urban scale. Here, our goal was to develop an urban network of pedestrian bridges which connected multiple towers to their urban context. We did this by selecting starting nodes from the tower system and incrementally growing them in their local context using specific forces and weighting factors to drive their pathways. We then optimized these urban pathways using evolutionary algorithm with fitness objectives towards high closeness centrality, high path efficiency, and a minimum displacement. And while these results showcased a series of bridges which were very optimized for their goals, it was really difficult for us to understand how pedestrians would actually use these pathways. And with that in mind, it was necessary for us to integrate a pedestrian simulation as a post-analysis tool to further understand these networks. However, these existing pedestrian simulations that we found lacked some key mechanisms that were really crucial for our project goals. They lacked vertical movement capabilities, they were limited to physics-based simulations rather than network-based ones, and most importantly, they lacked any social interaction considerations. With those flaws in mind, we decided to create our own pedestrian simulation plugin called Hive, which introduced social interaction as a key driver for pedestrian behavior. In this simulation, two agents come in close contact with each other, and their individual social levels are tested. The closer these values are, the more highly likely they are to interact. And the higher their values are to 1 as well, they are more likely to interact in that case. This probability is also guided by social global levels and a small level of randomness, which determines the difficulty for that social interaction. Here you can see a very simple example of Hive's pedestrian network simulation, which uses those social factors as the driver for the algorithm's behavior. This type of simulation unlocks a new potential for not only understanding how people use network systems, but also how you can use them as drivers for community gathering and socialization processes. So you can see here the process of setting the simulation parameters, allowing pedestrians to interact as they go about their pathways, and finish with some analyses and methodologies in that case. We ran this pedestrian simulation on 3 urban networks from our multi-objective optimization, which clearly show which pathways were more effective for travel and social needs, and which ones were remaining largely unused. All 3 of these networks were initially shown to be highly performative from our previous objectives, but when we implemented this social behavior as an additional benchmark, it was clear that some of them failed to facilitate those proper connections. And as a result, these studies showcase the impact of using social interaction as a driver of design.
So those, the previous examples we showcased how people's sociability can drive the initial design of an architectural space. So now let's take a look at the urban network we developed, which employs people's social interactions as a driver for change over time. So in our thesis, the urban network we developed was designed to connect multiple disjointed micro-urban networks and form a holistic macro-urban system. So we used 5 environmental data points to weight the existing road network system and create a context-oriented connections between multiple towers. Then we employed a shortest walk algorithm to locate a series of pathways. Along these pathways, we placed elevated multimodal corridors, which were designed to host various program and transportation types. While the design and implementation of these multimodal corridors were well informed by context-specific data and information, they failed to acknowledge the social nature of the people using them and the temporal nature of transportation. So therefore, we again utilized Hive's capabilities, but this time we used a cellular autonomous pedestrian simulation to introduce social characteristics to the agents, program, and existing context along these corridors. The agents' movements were determined using a 9-square grid, where adjacent where cells adjacent to the agent influence the probability that it moved in a particular direction. As Pooja previously showed, these probabilities were driven by the relationship between the sociability score of the agent itself, its surrounding program, other agents, as well as the context. So in the context of our thesis, we weighted the surface areas of these multimodal corridors based upon the sociability of the existing program and the program designed on the spaces, and Hive analyzed how agents would move and interact throughout that space. So by utilizing the output data from Hive, we simulated how the space may adapt over time by adjusting those input parameters of the programmatic arrangements and the context sociability. As we iteratively continued such a process, we generatively developed a well-suited programmatic arrangement which responded to people's changing sociability over time. Thus, a consideration of people's social interaction through Hive helped inform the locations for both future program as well as showcase potential for adapting existing ones. So throughout our thesis, we examined how a consideration of people's sociabilities, the way in which they live, move, and interact, not only influences the initial design, but can enable it to adapt and respond to changes over time. So we can never really know for certain how our environment would change now or in the far future, but by developing a built environment that can adapt in an age of climatic and ecological change, we can empower architecture and people to evolve together. Thank you.
I love the ingenuity of the adaptive spaces, and I noticed that there are little green trees around, and I wondered what the relationship between nature and the social dynamics were, given the density of the urban environment, whether the kind of the biological aspects or natural light and things like that were elements that you'd considered.
Mm-hmm. So in our simulations, particularly the cellular autonoma, we treated nature or public space as a program sort of element, and depending on really throughout the tower whether or not that was a priority in that particular area or space, we gave it more weighting, more priority, higher sociability score, and we did see that did draw people more congregated throughout those areas, and so that helped us inform throughout the tower where those elements would be located.